Hi and welcome back, guys. So now we continue on chapter 5 part 4, which is on the RTD of ideal reactors and the non-ideal flow phenomenon. Okay, so in this subtopic we will discuss on describing RTD in ideal reactors and also in non-ideal reactors, okay, and how to diagnose the faulty operations of your reactors, right? So for RTD of ideal reactors, so in describing the RTD in ideal reactors, we use plug flow and completely mixed flow to describe tubular reactors. Okay, so the plug flow model, okay, we use to describe tubular reactors, which including PBR, and for the CSTR we use the completely mixed flow, okay, to describe the characteristic of RTD in this chapter. So in this section we will use these two ideal flow pattern, okay, plug flow and completely mixed flow, to describe this condition of the reactors. Okay, in the plug flow, the assumption that we use in order to describe the characteristic of the mean residence time or other characteristic of RTD, okay, so we assume that the fluid, okay, enters the particle, the fluid or the particles that enter the system will exit from the system or from the reactor at the same time. This is the assumption that we use. So previously we know that the response curve has the same curve as CT. Okay, so now the RTD for plug flow model can be described by this equation, which is ET equals to del T minus T bar, or TM is actually your mean residence time. So this equation is the same one in your textbook, equation 5.24, right? And then when we convert it into dimensionless equation, so it will be this equation, which is described in equation 5.25 in your textbook. So it is E, this is like theta, dimensionless, this equation is dimensionless equation. So this is your residence time just now, times ET. So you will end up having this formula instead of this one for the dimensionless, okay? Right, so similar goes by variance, okay, this is variance, so we change it into the dimensionless equation, will become like this, okay? So this is the E curve for RTD for ideal PFR, and this is the F curve, right? Okay, so the next one is for RTD in ideal reactor for perfectly mixed reactor. Okay, so when dealing with perfectly mixed reactor, okay, so let's say we are taking mass balance of the tracer in the reactor. So you inject a tracer in the reactor. So this is actually in minus out equals to accumulation, VR dc over dt. So when you rearrange back, okay, and then we know that VR over Q is actually equals to your residence time or space time. This is like a standard normal equation, right? Tau is equals to this, what you have learned before, okay, in previous chapter, okay. So it is V over Q, right? Velocity over flow rate, okay. Right. So when you have this part, okay, so when you plot it, it will be this kind of curve where C naught is your initial concentration that goes into the reactor, and then you will find this curve. But when you are describing the ideal reactor, again, we use the E curve. Okay, so E curve, you see, this is what I'm trying to tell you just now. So you can see it is the similar shape, right? So from the E curve, okay, for ideal reactor, you can determine the residence time. Okay, so for perfectly flow mixed reactor, so the ET is actually equals to exponent negative T over tau or over residence time divided by tau, or residence time, right? So the ft will be equals to 1 minus exponential to the power of minus t over tau. So this one you can refer to your textbook, right? Okay, so these are the curve, the E and F curve for various flows. So this is the PFR, plug flow, and then this is to describe the mixed flow, mostly a CSTR. So actually this is a summary of the what that we learned before, right? So now I would like to go for the RTD. On how to use RTD for diagnose faulty operation. Okay, so how do you know whether your reactor is working ideally or not? Okay, so first we need to know what is non-ideal flow phenomenon. Okay, so all flows that do not satisfy ideal flow condition are called non-ideal flow. Okay, just now let's say we have two model to describe the ideal reactor, which is plug flow and also the perfectly mixed reactor. Okay, so in this subtopic, we will also use the same kind of reactor, but how we can know in that reactor we have this kind of non-ideal flow. So we have stagnant zone, channeling, and short circuit, or sometimes we call it bypass. And then we have also cyclic flow, uneven flow, and diffusion. So there are 5 altogether, right? So, right, from this curve, okay, so let's see. This is A. Okay, so you see this is an E curve. So this is actually how an ideal E curve that should be look like for the ideal plug flow reactor. So here we can see it's RTD for near plug flow reactor. Okay, so this is ideal reactor, and then this one is ideal perfectly mixed reactor or CSTR. Okay, so you know these two are example of ideal condition. Okay, and then this diagram C, we can see there are problems in the PBR. Okay, you can see here there are dead zone and also channeling, right? So again, so we can see here what is dead zone. Okay, sometimes the stagnant part in your reactor that is not moving out, what we call it dead zone. Okay, channeling is where sometimes some of your liquid taking shortcut and will exit the reactor at a faster time, right? Okay, so from diagram C, when we plot the E curve, it will be reflected something like this curve in D. So there's a channeling and later will be a dead zone, alright? Okay, so for diagram E, it's actually showing you the problem exists in CSTR or perfectly mixed reactor, where we have the dead zone, okay, and also some bypass. Okay, normally it's supposed to go through the stirrer and then only pass through the outlet. So this is like bypassing or short circuit. Okay, and then when you plot an E curve, it will be, this is like an ideal, the B diagram, but this one, if the diagram, if you have reactor problem where this is indicate bypass and this is indicate dead zone, and you see here this is a tailing. So I will explain further in the next slide on how to know what is the problem of the reactor, right? So giving you another example, this is some the example of having dead zone in PFR. So you can see the red area which shows you some dead zone. Okay, so and then short circuit, okay, bypass is in the CSTR. Again, this is like a channeling, some sort of a short cut, okay, causing problem. And then this is for extreme short circuit and bypass. So we're supposed to go through all the catalysts here, but somehow it took a shortcut. That's why we call it a short circuit, or also channeling or bypass, right? So for this slide, okay, so let's consider on CSTR. Okay, so this is an ideal CSTR, or ideal perfectly mixed flow reactor. So this is the kind of E curve that you're supposed to have with short tail, right? If your CSTR having problem for that zone, you see there is a longer tail here, right? And then similar goes in this y-axis, right? So stagnant region will cause the tracer material to remain in the reactor longer as it diffuses and out of the stagnant region, right? So the flow pattern of CSTR is equals to perfectly mixed flow. However, when stagnant present, okay, so that's why this tracer material remain in that reactor. Okay, so for the third diagram was supposed to be model SPFR with recycle and some dispersion. Okay, you see this actually is showing you and or indicate to you there's a recycle flow. Similar goes for this diagram in this slide. So the first one was perfect operation. So when you have a curve, this is like a perfect or ideal curve for perfect operation. So you can determine your tau or residence time from the graph. Okay, and then this is the reactors have bypass or channeling or short circuit, is the same thing. So the curve will be slightly lower like this, and then you can determine what is your flow rate and also the bypass volume. Okay, so bypass will affect the flow of the flow that enters and leave the CSTR. Okay, for that volume, okay, so this is where you can determine on the curve, you can determine what is the residence times of the reactors that have a dead volume condition. Okay, and then when from here you can know how much of the volume that is stuck in the reactor. Okay, so it affects the volume of the reactor for the dead volume, right? So this one is for tubular reactor. Okay, so the first one is actually a perfect operation for tubular reactor. So we can describe the residence time or space time is equal to tau equals to V over V naught. Okay, sometimes you use the V naught, sometimes you use Q. In your textbook they use Q. Okay, for flow rate, right? So when you plot the graph, you will have a curve something like this, right? So if you have bypass, okay, it will affect your flow rate, and then this will affect your flow rate. Your flow rate will be down, so your residence time will be bigger. Okay, and for PFR, it will affect for the dead volume, it will affect your volume. So when your volume goes down, it will make your tau also goes down. Okay, so that's why you have tau on that having that volume is smaller than the tau of ideal condition. Okay, so if you have this channeling, you have two peaks, right? So this is kind of question that I want you to try to diagnose the problem occurred in the PFR. So given to you earlier is this is the C curve. So after a few years, after 2 years, when they plot the C curve, it will be something like this. So you can see initially they have around the residence time maybe at 15, but after 2 years, residence times become smaller. So by looking at this, we can see that maybe the reactor is having a dead volume condition, because earlier we know that for a tubular reactor, so that volume will make your residence times become smaller, see? Right? Okay, so try to do this exercise and you will understand more on it. Okay, so I'll see you in the next video to discuss on the segregation model. Thank you.